Welcome everybody to week 5, day 1. It is functions day. So we're going to be talking about two things today. We're going to be talking about using functions. We're going to be talking about writing functions. And so first of all, what is a function? What is a function? Answer, it is a saved algorithm. How about that? How about that for a definition? So when you write code, you can write code and you can even copy and paste the code if you want. But if you want to reuse that code at different points in time, you put into a function. Now, if you are reusing the code immediately, you do a loop, right? It's like if you have some codes, and I don't know, let's just do something simple. My name is, I could just repeat it 3 times, I mean, I could just do this, right, and just repeat it 3 times. I could put it into a for loop and repeat it 3 times. One of the rules in computer science is don't repeat yourself, right? So this is one of the guiding principles. Don't, I know I've said it before, but don't repeat yourself, right? So a function avoids repeating yourself at different points in time. So let's say that at different points in time, you're going to be writing code that will be sorting numbers. Like you've got a bunch of points and you want to sort them left to right or something like that. You could write the code to sort them all left to right over and over and over again, but that's incredibly wasteful and you're repeating yourself. And there's a good chance that one of the times you're going to rewrite it and put a bug in because you type something in wrong. It becomes hard to test and hard to debug, and it's just a pain. So what we want to do instead is put all of that code, maybe it's 30 lines of code, who knows, into a function, and then we can reuse that code as often as we want. Now, the benefit of this is that very popular functions, I can type, are in the standard library, which is abbreviated as STUD, like that, or STUD, or STD, or STID. No. Okay. And so a lot of the things that you would want to do are already done for you. And what's nice about that is that you have smart people who've thoroughly tested it, have optimized it, have made it as good as they can. They've got implementations to do sorting for you, and they've got implementations to reverse a string for you, and they've got functions to do sine and cosine and things like that. Like, how many people here have taken like algebra and trig? Right, let's get a show of hands on chat. How many people here have written math formulas that involve sines and cosines and things like that, right? So how many people here want to compute a sine numerically themselves? Like if I asked you, float x is equal to the sine of some number, how many people here want to compute that themselves? Like use, I don't know, some sort of numerical approximation method, Newton's method or something. I don't know. Do you guys know even how to compute that? Like if you, not like having a table that's pre-computed for you, not having a standard function call, but actually like numerically approximating the answer of 320 sine of 323.12. Anyone? You have? Great. So why don't you write out the code for that? Now nobody wants to write out the code for that, right? Like that's just absurd, right? Like why write out all the code to compute a sine when you can do the following? Hashtag includes CMath. CMath has a bunch of math functions in it done for you. And you can just use the smart people's implementation of sine and cosine and things like that, right? So you can say x is equal to cosine of 0, which is 1, right? X is equal to the tangent of something, whatever. You know what I mean? So like these functions, all these trig functions exist. There's tangent and, I don't know, arctangent. And if you saw the list there, A cosine, H something, you know what I mean? So like all these trig functions exist. You do not have to write them yourself. Instead, you can avoid repeating and reusing all of this code by simply calling somebody's implementation that will tell you the trigonometric values of all these different functions. So that's nice. Okay. There's also, what else is there? There's like absolute value, which is like x is equal to the absolute value of negative 3.1. So with that, now that one you probably could write. You know, how many people here could write an absolute value like, you know, if x is less than, you know what I mean? Like, how many people with your knowledge right now, with 4 weeks of computer science under your belt, you could probably write a program that would like compute the absolute value of a number? Yeah, pretty easy, right? Like, you know, if x is less than 0, see out -1 times, you know, something like that. Yeah. So that one, you know, there's maybe a little, yeah, it's a little less typing, but it's not like this where like, you know, most people are like, I don't know, maybe I could do it. It might take me a month, might be buggy, I don't know. So there's abs, then there's like pow and exponents and logs. So x is equal to pow of 2 times. That means x is equal to 2 to the 3rd power. Okay. Now some students will write exponent like this. 2 to the 3rd power. No, this is not 2 to the 3rd power. This is valid C++. In fact, if you try scouting 2 to the 3rd, what you think is 2 to the 3rd power, it's not. It's XOR. But if you try outputting 2 to the 3rd power, you're going to get 1 as a result. And the reason for this is because the caret, the shift 6, the exponent symbol does not mean exponentiation in C and C++. It means something completely unrelated to it. And so 2 to the 3rd power, that's not what it means, is 1. And so many students have been very surprised by this. This is not right. And in fact, compilers will warn on this, right? If you try writing code this way, you're going to get a warning. Result of 2 to the 3rd power is 1. Did you mean this? You can silence this warning. Okay, so that is not exponentiation. This is exponentiation. Okay, so if we see out x here, then we will get 8. 2 to the 3rd power is in fact 8. Yeah, don't use that caret until we get to bitwise operators. It is not exponentiation at all. Python people in particular might have trouble with that one. So you guys all know pow, right? Like exponent, like pretty straightforward. How many people here know log? What does log do? What is the log of, I don't know, 10? Which base is that? You know. So logarithms are usually covered in like, you know, algebra 2 or something like that. And I never really understood them. Like, I mean, I understood, like, I can manipulate things algebraically. Like, if you write, you know, like log base 2 of 2 to the x power, you get x. Like I understand that, you know. But, like, I didn't understand, like, what they're used for. You know, why are they useful? And the way my brain works is that if something is not useful, like if I'm like, when am I ever going to use this? My brain just crumples it up and just throws it in the trash can, right? Like I remember it enough so I could like sort of symbolically manipulate it and do things like this and cancel out an exponent or something like that. But I never got when and where I'd actually need it. And I asked my teacher, I'm like, Ms. Anderson, you know, I think she married and became Mrs. Mead? Maybe? 8th grade? No. So yeah, 7th grade, 8th grade, my algebra instructor, you know, I asked her like, when am I going to use logs? Like when is this going to help me? She's like, well, if you have to use a slide rule, slide rules are based on logarithms. So you have to understand them. And I mean, I'm not that old. Like even when I was in middle school, like people had, you know, calculators for a good long time. So I don't even know if you guys know what a slide rule is, but these slipsticks, they're called sometimes. This is how people did like calculations back in the like 50s and 60s. So I have no idea how they work. Like, because, you know, clearly I didn't learn how to use them because I had a calculator, you know, and so if the only use for logarithms was, you know, knowing how to use a slipstick, and I own one. Like my grandfather gave me a slide rule, and I just never learned it. Because I had a calculator, and calculators are just easy to use. So, yeah. So then I got into college, and then I started doing computer science. Well, it's at the same time. And logarithms are everywhere in computer science. And I was like, oh, maybe I should have paid attention to these things when I was learning them the first time. So to kind of explain the use of a logarithm, and there's different log functions in the standard library. There's this one, which is a natural logarithm. There's log base 2. There's log base 10. The log base 2 of 8 equals is 3. And the log base 10 of 10 is 1. We're going to have to introduce a concept that is really more of a CSci 41 concept, but I find that it helps in 41 if you've kind of seen it a little bit in CSci 40. So let's say that we are, let me just scroll this off the bottom of the screen. We'll come back to it. Let's say that we're going to do something like we got a string, and it's filled with every name of every person in Fresno. In fact, when we get into vectors, this will make a little bit more sense. Well, let's say excuse me. Let's say it's got 1 million names in it, okay? And we wanted to print out all 1 million names. Like we do some sort of for loop, print I equals 0, I is less than 1 million, I plus plus. See out, whatever the name is. How many operations is this going to be? It's going to be 1 million, right? Like, so to speak. You're basically 1 million times you're going to do something. And so, thank you. So, in computer science, we call this an order n algorithm. In other words, as the amount of work we have to, n is the amount of work we have to do. So, if you're printing out a phone book, if you're printing out a directory of all people in Fresno, the amount of work you do goes up linearly proportionally to the number of names that are in the phone book. So, if you have a phone book with 1 million names in it, then 1 million times you're going to get the next name, print it to the screen, and repeat. Okay? So if you change this from 1 million to 2 million names in the phone book, then the amount of work you do doubles. So if you double the size of the phone book, the amount of operations you do doubles. It's a linear sort of relationship, right? Linear running time, we call this. Okay? And, a lot of algorithms are order n. Let me pull up a chart here. Let's go to CSI 40. Big O. And so if we have, just stop writing. Okay, let's try that again. So if n is the size of the problem, like the number of names in a phone book, for example, and this is the running time, the exact numbers don't matter, but basically for an order n algorithm, it's going to look something like this, right? So if you have 20 names to print out, you're going to do 20 operations. If you're going to print out 50 names, it's roughly 50 operations. And how long those operations takes doesn't really matter. The important thing is that there's a linear relationship between the number of names you're going to print and the amount of time that it's going to take to print it. This is very approximate. It's never going to be a straight line exactly. There's caching and different other things that will cause it to wiggle a little bit, but this is what we call a linear algorithm. Now, let's say that you've got 1 million names in in Fresno, but they're not sorted, and you want to put them in sorted order, and so you have to do something like this, or like 1 million times you're going to go through those 1 million names and find the next one that's alphabetically, up, so to speak. So the first name would be AAA Towing, AAA, right? And the last one's going to be Zebra Zoo Animals or something. I don't know. Do you guys understand? So 1 million times, you're going to do a search from the top to to the bottom. And I'm not going to write the code here, but basically you're going to like find the next alphabetical name. And that might be, you know, a little bit of code. You guys understand? So we've got, you know, like if you've got a deck of cards, you could just put all the deck of cards on the table and you'd be like, all right, find the ace. Okay, there. All right, now find the 2 of spades. Now find the 3 of spades. You go through all of the cards every time. How many operations is this? What is 1,000,000 times 1,000,000? How many operations is this? Roughly. You know, and again, this could be 5, 6, 10, it doesn't really matter. Point is, like, we're trying to get a feel for how many times this loop's going to run. Yeah, so it's going to be like a trillion, I think. Is that right? Thousands, millions, billions, trillion. Yeah, it's going to be like a trillion operations. And then if we change this to, you know, if we add more people to Fresno, if people move in from the Bay Area because housing prices are expensive over there, if 1 million more people move into Fresno, if we're going to sort all the names of people in Fresno and we go from 1 million to 2 million, now rather than doubling our work, we're squaring our work. You guys see that? So the amount of work is going to go up 4 times. It's going to be 4 trillion instead of 2. Do you guys understand? So for every doubling, you do 4 times the work instead of twice the work. Does that make sense? And so this is something called an order in squared algorithm, which goes up quadratically or polynomial time, we call it sometimes. Then even worse than that, and these curves are not exactly to scale, is 2 to the n. Now this looks very similar to this, right? But they're as different as night and day. So order 2 to the n algorithm says for every name you add to Fresno, you have to double the amount of work you're taking sorting it. So what would be an example of a 2 to the n sort algorithm for the names of everybody in Fresno? How about we try listing every possible way of printing the names of people in Fresno, right? And then we pick the one that's sorted. So for example, if we have 3 names, we have Alice, we have Bob, we have Sydney, we can print it ABC, ACB, BAC, BCA, CAB, and CBA. You see that? And if you have 4, then it's all of these, you know, but double the n, you know. And so for every name that you add, you can write every single possible combination of names and then look at them and be like, okay, that one is the sorted one. It is a very inefficient way of sorting. It is tremendously inefficient. Have you guys ever heard the story of the smart-ass vizier that got his head chopped off? He did a favor for a king, and the king's like, what do you want your reward to be? And the vizier said, every day, I want you to put rice on this chessboard following a certain mathematical pattern. On the first day, I want you to place 1 grain of rice. On the next day, I want you to put 2 grains of rice. The next day, you double it again and put down 4 grains of rice. And the next day, you put down 8. And, you know, we'll just follow that pattern. And the king's like, ha, ha, ha. Stupid vizier, I would have given you half my kingdom. Ha, ha, ha. And then by the time, you know, by the time you got to like the 20th square, you're talking about 1 million grains of rice. The next day is 2 million grains of rice. The next day is 4 million grains of rice. And so the king just chopped the guy's head off to, you know, keep himself financially afloat. So how rude. Yeah, that's the funny thing. The math person's like, aha, I pulled one over on the king. And the king's like, aha, I've got a trump card called sword. And I win. So order to the n is bad. This is a very bad running time. If you have 1 million people in Fresno, 2 to the millionth power is some monstrosity of a number. It is unspeakably, unimaginably large. Even if you just had 100 names you're trying to do this way, 2 to the 100th power is like much more than the atoms there are in the universe. And that's just for 100 names. That's not even like that big a number. Like computers should be able to sort 100 names. But if you're trying to do it by just writing down every possible combination of names, it's actually worse than that. Actually, this is every possible combination. Sorry, it's actually even worse than that. My bad. It is order n factorial, right? So it is absolutely, positively, astoundingly bad. It is ridiculously bad. Now, why am I mentioning all this? Well, so 2 to the n is bad, right? You know, if you do something like this, it explodes so quickly. No computer could even handle sorting 100 names that way, right? Here's the kicker. This is why I'm mentioning it. Because logarithm is the opposite of exponentiation. So order log n. So with this, for every additional name you add to the phone book in Fresno, you have to double the work you do. For this one, it's the opposite. For every doubling of names, it's the opposite. For every doubling of names you add to the phone book, you only have to do one more step. That's really good. So if you go from 1 million names in the Fresno phone book to 2 million names in the Fresno phone book, you only have to do one more operation. For example, binary search, which is how most people read through phone books if they know what a phone book is. Right, so when you guys, if I gave you just a list of names that are all sorted, would you, if you're looking for like Luke Olson in the phone book, would you start in the A section and just start going like AAA towing? That's not Luke Olson. AAB towing. That's not Luke Olson. Would you just like read through the A section and then read through the B section? And then, I mean, if you're getting paid hourly, absolutely, don't let me stop you. This is how the DMV operates, I think. They type in my name and it takes 5 minutes for the system to find me. And I'm like, what kind of dumb programming, you know, like, are you doing a linear search? Like, are you literally like, because that's the only thing that makes sense to me, right? Is that like linear searches, you look at AAA towing, AAB towing, you know, you just started, you know, you just alphabetically go through every person in California until you find the person, right? And so if there are, you know, 30 million people in California, you have to go through 30 million records, worst case. And the worst case, by the way, is what the O means. The O means worst case scenario. Right? So you're searching for somebody and their name is the last in the phone book. Whichever order you look in it, they're last, right? So do you guys understand that? Like linear search? So like if there's 30 million names in California and you just start alphabetically going through all of them, you know, eventually you'll find them, but they could be last. And you might have to go through all 30 million records to find them. You guys with me on this? Now, compare that with binary search. So with binary search, the way that most people read a phone book, if you guys know what those are, is you open the phone book to the middle, right? And so you're going to open it to the middle and you're like, oh, okay, I'm on the K section. And Olson is to the right of the K section. And so what you can do is you can sort of metaphorically rip the phone book in half and throw the half away that doesn't have Olson in it, right? All the A through Ks, the AK section, is gone. We just ripped it out metaphorically, thrown it away, and then we repeat. So of the remaining names, which are now K through Z, we open it to the middle, and we're like, oh, this is the S section. Okay, well, O is to the left of S, so we rip out S through Z, throw them all away. With every step, we're throwing away half the names in the phone book. That's why if you go from 1 million names to 2 million names in the phone book, it only takes one extra step, right? Because you're getting rid of half the names with every iteration. And so if we had 30 million people in California, 30 million, 30 million people, if we take the log, no, that's not the log base to... There we go. Okay. 30, 1, 2, 3, 1, 2, 3. We're going to do the log base 2 of that. 24 steps. Okay, roughly. So in 24 steps, you can find any record in California, assuming you're looking by name and it's sorted by name already. Do you guys see the difference? 30 million versus 23. It's a pretty huge difference in running time. And that's why logarithms are so important in computer science. Logarithmic running time algorithms are fast, are super, super fast. They are as fast as exponential algorithms are slow. You understand? So if the smart ass over here had said, for every doubling of squares, you're going to give me one more rice, you wouldn't get very much rice. Yeah. All right, you get one rice on the first one, and then 2 later, and then 4 later, and then 8 later. Oh, perfect. There you go. There are your 5 grains of rice. Don't starve. Right? So for every doubling of work, you only have to do one more thing. And so that's why logarithms are so important in computer science. Okay? You guys understand what I mean by binary search? Like flip to the middle, see which way the name is, and then flip to the middle of the remaining part. Is that understandable? Logarithms, algebra. Sounds like a rapper's name. The logarithm. Yeah. No rappers in here. None of these look. Yeah. Very, very entertaining, which kind of explains why my middle school self wasn't too into it. Okay. So that's a little introduction to Big O. All right, so we got log base 2 of 30 million here. Yeah, there you go, 24 operations. Okay. So power exponents, logs. All these are pretty straightforward. There's a lot more math functions in there. Ceiling, rounding, floor. These are some other ones. So rounding functions. So for example, x equals ceil of 5.4 gives you 6. So ceil gives you the next integer above the current number. And then floor, which is kind of pointless. Floor is going to give you 5. It's the first integer below the current number. It's pointless because you could just do that, right, and get 5 also. Oh, sorry. If we made this an integer y. That's right. If we're saving the results into an integer, then oh, because I'm printing x, not y. Yeah, okay, fair enough. Yeah, but setting it to an integer is the same thing, effectively, as a floor, at least for positive numbers. And then you've got round, which rounds to the nearest whole number, which in this case is 5. 5.5 rounds to 6. Okay. Round is pretty useful. Ceiling and floor, I guess I've used. I can't really think of any examples of when I've actually used it, but rounding certainly is a thing. Then of course the most useful math functions, you've got the Bessel functions, of course, right? Right, so you've got all these different Bessel functions. You got the cylindrical Bessel function, IF, IL, JF, JL, KF, KL, IJ, and K. I don't think I need to explain these to you guys. I think you're pretty good with Bessel functions, right? 5.3, and I don't know, 2 or something, right? I think we all got what's going on there, right? There you go. See, I mean, everybody was about to say 15.1992, right? Right? Like I think we all got that. We don't need to go into too much detail. What is that? You're not going along with the joke, Caesar. Uh, so I don't think I know a single person that's ever called one of these functions, but they're in there, you know. So it computes the regular modified cylindrical Bessel function of nu and x. There you go. Everything's explained now. And if you ever want to look up C++ functions, the CPP reference website is... Alrighty then, yeah. The CPP reference website will explain everything. And so, you know, you got all these different, you got spherical Bessel functions, you got the Riemann-Zeta function, of course, we all know what that does. The Hermite functions, the Neumann function. Like, I like you don't even need to ask me about these. Like, I think everybody knows what the Riemann-Zeta function is, right? Yeah. Okay. Can you put the website in the chat? Sure. Yeah. If you want to look up the zeta function, I think the zeta function is like counting primes in a certain range. Complex analytic number theory. Zeros in the critical. Like, I mean, okay. I think with this on the screen, I can just leave it at this, and you guys like this is self-explanatory, right? Like, I don't think I need to explain any of this to you. Like, it's just like you just look at this, you're like, oh yeah, I know what it is now. This is everything I need to know about the Riemann-Zeta function. Right here. One screen. Exactly. Easy. Your average chess opening move. Yeah. The pole and at 2 zeros on the critical line. Whatever the hell that is. Yeah, there's something about, it's like prime. Yeah. On the number of primes less than a given magnitude. Yeah. So basically the zeta function, yeah, tells you how many primes there are less than a given number. So if the zeta of 5 would be 3, right? 2, 3, and 5. So, or less than. So the zeta of 6 would be 3. So you have 2, 3, and 5. Something like that. So, yeah. So there's a lot of special mathematical functions like that I literally have no idea what they do. Bessel functions are used in like drums, like to simulate standing waves and things like that. Is from what I understand. Like, do not ask me to explain it. Okay. So yeah, this is how you use a function. Okay. And the basic syntax for using a function is you give the function name, you give an open, smooth parentheses, parameters if there's any, and a close parentheses. And so, for example, if we, and you can put them just directly in here, like cout the cosine of 0, right, so like that. You can embed them into other things like that. Pow of, I don't know, 5 squared or whatever. So, yeah, the cosine of 0 is 1, 5 squared is 25, right? So what happens when we call the function, okay? So when our flow of control, when our execution gets here, when it gets to that line, it's going to pause main. Like main, you know, you can have different variables like this, you know. The value of x is saved. Like it saves all of your variables. It just kind of puts main on pause. And then it's going to jump into whatever code you're calling. In this case, it's going to jump to the code for cosine. And if you guys really want, I can show you what the code for cosine looks like. Are you guys... You guys want to see that? Yes. You asked for it. So, do you guys know how include works before I show you the stream? When you hashtag include something, it's actually copying and pasting all of that code into your code. So right now, how many lines of code do I have? Word count by line, main.cc, 35 lines of code. If you compile your code with the -e option, this will actually show you what your code looks like after it has copied and pasted all of that horrible looking header code into your code. So this is what is actually you're actually compiling. After all the hashtag includes are done, this is actually your main.cc. And there's a lot of stuff in here, and it's not very readable. I don't know. So, yeah, look at this thing here. Look at that. Return type of _ lin, 0 less than type of lin, -1 is a typecast, or built. That is one line of code. Yeah, that is imagine if there's a bug in that. You know what I'm saying? Imagine there is a bug in this code somewhere. How many ternary operators do they have in here? There's at least 2 that I've seen. There's a ternary operator there, ternary operator there. Those are like if statements. Allow you to put both sides of an if statement into a single line. That is yeah, that's a line. That is a line of code right there. It's in the mbsrtowcs function, which again I'm sure I don't need to cover because we all know what that is. So I was gonna do cosine. It's gonna do cosine. Okay, so cosine calls _ cosine. Well, that's very exciting. Okay, well, there is your cosine function. Oh, no, never mind. Cosine is just declared extern. So it's actually written somewhere else. So the source code for cosine is sort of not appearing in this movie, basically. A lot of cosine functions, by the way. Maybe here. Cosine, here we go. Return, okay, so it's using the compiler's built-in cosine function, which doesn't really tell us very much about how they're actually doing the cosine. But you want to know how many lines of code we are up to now? 58,000. So our little 35 line of code program has ballooned to almost 59,000 lines of code. And that's all the includes, right? All the CMath stuff is in there. All the IO stream stuff is in there. And I included, I think, algorithm maybe, or vector. I don't need vector. Get rid of vector. It's now 54,000 lines of code. So those includes add a lot of lines of code to your code. And will actually slow down your compilation time. If you want, you can include the entire standard library. Let's time this and see how long this takes to run. 0.069 seconds. All right. Let's include the entire standard library. Huh? Include bits slash std C++ H. Don't need you anymore. Don't need you anymore. This is the entire standard in one file. Okay. And so if we compile it now, we have 165,000 lines of code. Okay. And the compilation time is noticeably more laggy. It went from 0.6 seconds to 1.3 seconds. Yeah, a lot of people look down on this. It's non-standard for one thing. This is not actually in the C++ standard. So if you do this, you're tying yourself to a particular compiler that does implement this. Coming in the year 2023 is the ability to import the standard library. But we'll see when that actually gets implemented. It should give you all the benefits of getting to pull in everything in std without having to use hashtag include, which is a very ugly and gnarly and slow system. Hashtag include literally just copies and pastes files into your file. It's not intelligent at all. It's not very good. But, you know, sometimes I do see students use this because they just can't keep track of like what things are in what libraries. I don't recommend it. Okay. we have before IOStream and CMath, I think. Okay. Okay. So the benefit of using standard library functions, benefits, usually they're pretty fast, pretty reliable. Like, I don't think I've ever found a bug in something like Sign or POW. Like, I don't think so. In Students Code, yeah, found lots of bugs over the years. But in the standard library, it's pretty good. It's pretty well tested. There's some obscure corners sometimes you'll run into where you might find bugs. Usually the bugs are, though, in the newest stuff. So like right now they're writing the C++ 23 code. Well, they're adding to the standard library all the C++ 23 stuff. And when it's kind of cutting edge, like you'll get weird compilation bugs and just random things won't work and things like that. Pretty fast, pretty reliable, and it's just one call away, as they used to say on the phones. They're just a call away. So this is called a function call, right? And so if you want to use sine or cosine, you don't have to write it yourself. It's pretty fast, and you just call the function, and you're good. The syntax, again, is name of the function, open parentheses, parameter list, close parentheses. If you've got more than one parameter, then you put a comma between them. So that's 2 to the third power. Okay. Modules is coming. Yeah, they're coming. So I'm excited. I'm cautiously optimistic. And, you know, worst case scenario, they're worse than hashtag include, and you can just keep using hashtag include. That's not going anywhere. So, but yeah, being able to import std, this excites me more than it should. The ability to just import the entire standard library and just have the compiler figure it all out. And soon it's coming. Okay. Yeah, matrices are coming. MD span. Yeah, there's a lot of cool stuff coming. All right, now we're gonna learn. Oh, I deleted the wrong one, didn't I? Now we're gonna learn how to write our own functions. Okay. So rather than all of this stuff, we're gonna write our own. So float Bob is equal to f of 10. Something like that. Here's how you make a function. Okay. So I'm making the C++ equivalent of f of x is equal to 2x minus 7. So let me explain it to you. First up is the return value. So the return value is float. So we are going to return a floating point number as our return value. That is the key word here. Okay. The second thing is the name of the function. The name of the function is f. Why are functions always called f? In computer science, they're not. We actually tend to give functions more useful names, like sil underscore Bessel. Okay, maybe not. They're not useful. But in algebra, for whatever reason, it's always f of x. You know, and if f of x is taken, then it's g of x, and if g of x is taken, then it's h of x. And after that, Lord help you. We've run out of letters at that point. Maybe you have f prime or something like that. F hat. So the name of this function is f, but I can call it anything I want. I can call this function, you know, fluel, whatever. That's fine too. Okay. The parameter list, it then has this parameter list inside of parentheses. Has one parameter, which is x, which is a float. Okay, so what happens when we call f here in main? When we get to this line of code in main, Main is paused. All of main's variables are saved. It's paused, and then it jumps up here, and it passes in 10 as the value of x. So this is creating a new variable called x. X only lives within the scope. A scope is like a matching pair of curly boys. The variable x only exists between those two curly braces. If I come down here and try scouting x, I get a compiler error. And the reason for that is because x doesn't exist here. X only exists between these two curly braces right here. Another thing to note is that the function is above main. A lot of students try writing their function inside of main because so far everything that we've done is inside of main, but that's not how functions work. Functions are reusable bits of code. We can call them over and over again, right? Like this. That's why we put things into functions, so that we don't have to keep repeating ourselves. We don't have to keep repeating ourselves. We don't have to keep repeating ourselves. We can just put all of our code. This is a very simple function. But even still, I don't think I'd want to write 2 times x minus 7 over and over again. But some bigger functions like sine and cosine, that's 80 lines of code maybe, I don't know. And so you definitely don't want to have to write 80 lines of code every time you want to do a trig, identity or something. So functions allow you to write your code once and then reuse that code over and over again. And that puts all of your code in one place. If you have a mistake, you only have to fix it in one place. You don't have to fix it in 7 places. It cuts down on the overall size of your program because rather than repeating this equation over and over again, you just call f. You're reusing the code over and over again. You're not repeating the same code over and over again. If I had to change this to be 2x minus 70, I would have to go through and search and replace every place in my code where I was using that equation. But by putting all these function calls in here, what happens is when we get here, it pauses main, it jumps up here, passes in 20 as x, it does some computations, 2 times 20 is 40, 40 minus 70 is negative 30, and then it's going to return negative 30. And so what happens is that this f of 20 here, this function call here, is negative 30. It's as if I had written negative 30 there. The return value of the function replaces the function call. You guys understand? So in algebra, you pass a value in, you pass the parameter to the function, and you pass x in, right? In this case, we were passing in 20. 20 goes in, and then the thing does some computations, and then the return value comes back out. Usually we call it like y for whatever reason. And so in this case, the return value coming back out is marked by a return command. The return command says, return this value from the function. And that literally takes the place of the function call in your code. And in fact, the optimizer, if you compile your code with the optimizer turned on, it will do this. It'll actually just delete the function call entirely because it takes time and effort to do a function call. It slows your code down. It's like, I know what the answer is. I can do algebra, the optimizer says. If you pass in 20, you get 2 times 20 is 40. 40 minus 70 is negative 30. The answer is always going to be negative 30, and it'll just put the answer in there. And it'll do that for each one of them. There's something called an optimizer, and you can compile your code with the optimizer on like this. G++, G++-03, compile your code with the optimizer off like this. G++-O0 main.cc. So anytime you're going to benchmark your code, if you're going to see how fast your code is, if you're not turning the optimizer on, your timings are worthless. Because with the optimizer off, the compiler generates really terrible assembly code. And so you always, whenever you're doing benchmarks, you would always want to compile it with the optimizer turned up fully. Like this, and then it'll just do things like eliminate a function call. Or if you have a for loop, for int I equals 0, I is less than 1, I plus plus, cout high. How many times is this for loop going to run? By default, the optimizer is off entirely. You're not going to notice any difference in correctness or passing test cases or anything like that until you get to more advanced computer science classes where we will actually start a timer and kill your program after 3 seconds. And so if you don't have the optimizer on, you might take 3.5 seconds, out of time, 0. But none of that's in CSci4. Yes, by default, the optimizer is off. So how many times is this loop here going to run? The loop will run once. Okay. So do I need all this overhead? Do I need the integer I equals 0? Do I need to do the comparison here? Do I need to do the increment? There's actually a lot of things that go into a for loop. You have to make a variable and initialize it and do a comparison and have a go-to that goes up to the top. Do I need all of this rigmarole? What do you think? If I just deleted this, it's the same code, right? And so that's another thing that compilers will do. They'll do things like that. They're like, that for loop's unnecessary, and they'll just delete it. Or they'll do things called loop unrolling, where if you have like a for here, it's like, we don't really need that for loop either. We can the optimizer will just do this for you. It'll unroll the loop for you. Then you don't have all the overhead of the loop. Nice. Making an optimizer is incredibly complicated. It's fun, but it's very complicated. You're probably not going to encounter that until grad school. Typically, you do compilers in your junior year, but you usually don't do optimization. Optimization's pretty advanced. I mean, I guess there's some easy optimizations, but like really getting into it is like graduate level compiler stuff. And so yeah, the compiler will just be like, nah, it's just YY3P. There you go, done. But the nice thing is you don't actually have to change your code, right? It's like if you're worried about optimizing your code, no, don't. Write your code like this. You know, you're gonna have 6 iterations. You're gonna have 6 iterations. Yeah, write it like this. The optimizer will get rid of it for you, so you don't have to worry. Okay, so what we're gonna do now is we're gonna have you guys implement some algebraic expressions. Okay, so you can't have 2 functions with the same name. So like you can't have 2 functions named f. Watch what happens. We get an error. Redefinition of f. Right. So I want you to call them f1, f1, f2, so on and so forth. Okay. And the functions that I want you to write, please, something like that. Right. So the functions I want you to write are these. F1, you're going to basically do the algebraic equivalent of f of x. I don't need 2 signs here. F of x is equal to 5 minus 3 times x. F2 is f of x is equal to sine of x divided by 2 plus 3. Just make it set up here. F of 3, we're going to do 2 parameters. We'll see if you can figure out how to do that. It's equal to x plus 1 divided by 2. Just averaging 2 numbers, basically. F of 4 is going to be f of x is equal to power 2 to the x power minus 1. Okay. So we're going to mix in a little bit of using the functions. You're going to be writing some functions. And so this is all placeholder code here. So all right. So I'm going to give you guys, what time is it? 2:30. Got like an hour left in class. So I'm going to give you guys till 4 to work on this. Okay. And then we're going to do one more function after this. You know, at 4 o'clock. Maybe I'll just give it to you now. Yep. So function 5 is going to be f of s, and it returns true if s is a palindrome, false if not. So it's going to take in a string s, and it's going to return true or false. This function is going to be like bool, like is palindrome, like that. And so you're going to write a function called is palindrome. It's going to take in a string. If it's a palindrome, do you guys know what a palindrome is? It's a word that's the same forwards and backwards. So for example, race car, true, it's a palindrome. Tool, it's not a palindrome. Taco cat is a palindrome. Do you see that if you read it forwards and backwards? Like if I go backwards, T A C O C A T, taco cat. And of course, my favorite palindrome, which is a man, a plan, a canal, Panama equals true. So that's a fun palindrome. Okay. So I will just give you guys until the end of class. So we got an hour left. If you get all 5 of these done, test your code, see out. If you want, bool alpha is there for you, is palindrome taco cat. Bool alpha means print true and false rather than 1 or 0, which is the default. And so you're going to make a function called bool is palindrome. It's going to take in a string and s. Okay. And I will just leave the thing up here. And I will return at 4:30 and show you guys the answers. If you guys finish all of them, post them onto the chat. You can bail out. Okay? And if you need help, I'm here. And it looks like Ben Corelli has taken off. So just send me a message if you have questions about any of these. Okay? So I'm going to pause the recording now. I'll come back in an hour. And welcome back, everybody. Let me do the answers. So the good news is, for the first one, we can simply literally type what you're supposed to type, which is 5 minus 3 times x. Oops. Let's put it on the side there. For F2, literally, yeah, that'll work too. For F3, we're going to take in 2 parameters. Now, you might notice that with the second parameter, you have to do a comma separated list there. So all the parameters go inside of the smooth parentheses and put a comma in between. For this one, we want the average of x and y. One thing you got to be careful for is that parentheses, without it, you're going to get an order of operations problem. This is going to do y divided by 2 prior to doing the plus x. So you want those parentheses on there so that it'll add them together and they give you the average. And now for the palindrome, this is one that I got the most questions on, okay? So there's, I don't know, maybe 3 different ways I can think of checking for a palindrome. One way is to reverse the string and then compare the strings, right? So you can say string s2 is equal to s, reverse s2 dot begin, s2 dot end. That'll reverse the string. And then return if they're the same. This is reverse is found inside of algorithm. Hashtag include algorithm, and there we go. So that is all it takes to do a palindrome. Now, most of you guys were doing things with like for loops and things like that. And so if you want to do it with a for loop, you can do something like this, where you say for int I equals 0, I is less than s dot size. Now, you do s dot size divided by 2, because what we're going to be doing is checking the first and the last, and the n1 and n1. We're checking every pair of characters, so we only have to do the first half. So if you do the whole thing, then you're just checking the back half again, which you've already checked. So you just do the first half. If we have 7 characters, then it's going to do the first 3, and then the back 3. Compare those. The middle one will obviously match itself. So if s dot at I, so the first time through the loop, that'll be 0. That's the first character. Does not match s dot at s dot size -1 minus I. So the first time through the loop, I is 0, right? So if you have 7 characters, the characters range from 0 to 6. The index 0 is the first index 6 is the last one. So that's size -1. Pull it in by 1. Then every time I goes up by 1, it goes 1 to the right for this one, and it goes 1 to the left for this one. And you check to see if they are not equal. If any of them are not equal, then you return false. If all of them are the same, then we're going to return true. And that, my friends, is that. So that is functions. We will pick it up again on Friday. Hope you guys had a great time. Post all of your solutions, whatever you have, onto the chat channel now, and let me know how it goes. So if you didn't get all of it, don't worry about it. It's just good for you to think about it, to work with it, to try and figure it out. This thing, by the way, is not something that a lot of students get right the first time. So you really have to sit there and sketch it out in pen and paper. I'm like, okay, the first time it's 0 and 6, the next time it's 1 and 5, the next time it's 2 and 4. And so you can figure out that algebraic relationship every time we go up by 1 this way, we come in this way, and work it out. Yeah, these look good over here. So I'm just going to say, well done, everyone, and see you on Friday. Peace.